Hello, my name is Koliah. So I'm going to show the simulation process for part A in module 2 PSpice Lab. So this is the RC circuit. This is V source, the V pulse. We use V1 is 0, V2 5, TD0, TR1 nano, TF1 nano, PW 0.5 milli, period 1 millisecond. And then we have R1 10 kilo ohm, C1 0.01 microfarad. We have repop here to obtain the voltage from this capacitor. The graph will be voltage versus time graph. We analyze, we create netlist, we set up it, click function, print step 0.5 millisecond, final time 1 millisecond. And then we simulate, we obtain a uniform uprising and falling graph. To obtain the value of voltage for each tau, for tau to 5 tau from, and then for the charge and discharge of the capacitor, we use the toggle cruiser, mark at each point of the tau and mark label to obtain the value of voltage for each tau. Then you can save it. Moving on to the second circuit, RA circuit. We also use V pulse, and the V2 is we change it to 5.31. This is because V equal to I over R equivalent, and the PW equal to 12.5 microsecond, and the period is 25 microsecond. As it was given in R out 50, R1 12, L 2.4 milli, RS 1 kilo, and we have a current probe at the L because we want to obtain the current value. We analyze, create netlist, we set up, transient again, print step 1 microsecond, final time 25 microsecond, and then we can simulate. Also, we will obtain a uniform uprising and falling graph. What we want to obtain the value of current at each period, for example at 5 microsecond, how many current, we use the same method as the RC circuit just now. So moving to the third circuit, it is the RLC circuit. So we have R1 20, L 10 milli, C1 2 micro. We have I prop at L also for obtaining the current value. T close is 0, and we use a VDC voltage source 21 volt. And then we will obtain a current versus time graph. We create netlist for this, and then we set up the transient, print step 0.2 millisecond, final time 10 millisecond, and then we simulate it. We will have a underdamped graph. To save this data, you click file and print, select which one you want to print, press OK, select the folder you want to save, label it with the correct label, save, and you can obtain graph in the form of a PDF, as you can see here. So you need to store it in a file, the data, for easy to manage it for the report. So that's all from me. Thank you.
Good morning, my name is Wong. I will present about the PAPI RLC series resonance. For the procedure, we must set up the schematic diagram firstly. Secondly, we must set up the AC voltage source of the circuit. Thirdly, we must set up the AC switch and noise analysis by set up the start-up frequency and end frequency. Fourthly, simulate the graph. And lastly, trace plot for resonant frequency, lower frequency, and upper frequency. For schematic diagram, we set the AC current source by setting DC equal 0 watt, AC equal 1 watt, V off equal 0 watt, V amplitude equal 1 watt, and frequency equal 10 kHz. After that, we set up the schematic diagram. We put the current marker to capacitor, inductor, and resistor to make sure the current across capacitor and current across inductor and current across resistor. Before simulate, we click on analysis setup and click the AC switch and noise analysis, and we set the start frequency with 10 Hz and end frequency with 10k Hz. After simulate, we will get this graph. Next, press on trace port and plot the lower frequency F1 equal 5.1811k Hz, and then resonant frequency Fs equal 5.685k Hz, and then upper frequency F2 equal 6.1811k Hz. From the graph, we will get the resonant frequency Fs equal 5.685 kHz, and then half power frequency F1 equal 5.1575 kHz, and then half power frequency F2 equal 6.153 kHz. And then we calculate the bandwidth of the graph by using F2 minus F1, which we will get the bandwidth with 1 kHz. Next, we calculate the quality factor by using resonant frequency divided by bandwidth, and then we will get 5.685 quality factor. So that's all for the ILC series resonant simulation.
Good morning. I'm Yap Zishan from 2B EKG Section 5. So today I'm going to explain about the Part C for Module 2, which is Parallel RLC Circuit. So first of all, we're going to have a look at case 1 first, which is R equals to 240 ohm and XC equals to 240 ohm also. So first we need to change this reactance value to capacitance value first. So we can do it by using the formula XC equals to 1 over 2 pi FC. So after doing all the calculation, the capacitance value obtained is 13.26 microfarad. Okay, so then we have to change the parameters set up here. The transient, we set the final time as 50 millisecond, and now we can start the simulation. Okay, so here's the waveform for case 1. So we remove the voltage waveform here first, and we standardize everything to positive so that we can analysis it, have a better look at the whole current waveform by changing it to positive. Okay, and then we add another plot to the window for voltage, since the lab sheet want us to find voltage waveform for V source also. Okay, so here's the voltage waveform for V source, and here's the current waveform. So first we need to plot the peak values first. We can do it by using the cursor feature here, display, and then we move it. Okay, here's the peak, and then we plot, label, and also mark. And then we'll proceed to current. So I'll only demonstrate for IC1 since all of them are use the same step. So IC1, okay, so here's the peak current waveform for IC. So we mark also. Okay, so the same step will be applied to IV1 and also IC1 waveform when we want to find the peak current. Okay, so then after obtaining this peak current, we are going to compare it with the calculation value and then do analysis. Okay, so when observing the current waveform here, we can see that the capacitor current waveform is leading the current waveform for both IV1 and also IR1, which is theoretically correct. Okay, so basically C view, right, for capacitance, the current waveform is going to lead the voltage waveform. So as we can see here, the capacitance current waveform is also leading the IV1 and so IR1 also. So it's correct. Next, we're going to have a look at the case number 2, which is R equals to 336 and XL equals to 480. So like just now, we need to change the XL here to inductance value. We can change by using the formula XL equals to 2 by FL. Okay, so after doing all the calculation, I'm going to open the circuit first. After doing all the calculation, the inductance value obtained is 1.53 Henry. Okay, so in order to prevent any sort of simulation error, a 240 ohm resistor is added in series with the L4 here, which is 1.53 Henry to prevent the simulation error. Okay, so please take note now. Here's a 240 ohm resistor is added. So it's like just now, we start the simulation. Okay, so here's the waveform. Like just now, we also remove V first and change all the current waveform to positive so that we can have a better analysis. And then we add another trace since the lab sheet wants us to find the voltage waveform for voltage source also. So we plot trace, add trace, V equals to V2 positive. Okay, so here's the voltage waveform for the voltage source and the current waveform for V2. R4, which is IR4, is also the inductor, the current flowing through the inductor branch, as you can see here, and also IR2, which is the current flowing through the register branch. Like just now, we have to use the cursor to plot the peak value for voltage and also current. Since there's not enough time, so I'm not going to demonstrate it. And then after plotting the peak value, we're going to compare it to the calculation. Okay. So as we can see here, the current waveform for the R4, which is inductor, is lagging when compared to the current waveform for IV2 and also IR4. So theoretically, this is also correct since for inductance, the current is always lagging. So yeah, this thing is also correct. So we have a look at case 6, which is R equals to 240, XL equals to 436, and XC equals to 320 ohm. So there's 3 branches and they will be connected parallel. So we need to change XL and XC into L and C value first, like I've explained earlier. Okay, so now we're gonna have a look at case 6 circuit. Okay, so here's the circuit for case 6. So there's 4 branch, one for R, one for C, and also one for L. Okay, so like just now, a 240 ohm resistor is added in series with the 139 Henry inductor to prevent any sort of error. And then yeah, the current probe are placed to obtain the current waveform. So simulation is started. We change everything to positive. Okay, we change everything to positive, and then we can have a look at the whole current waveform. So now we need to plot the peak current for all 4 of these waveform and then compare it to calculation. And now as we can see from the waveform here, the current waveform for capacitance is leading the current waveform of V2, resistance, and also IR7. Means the current waveform for the capacitance branch is leading the other 3 current waveform for other 3 branches lah. So this is also correct theoretically, since the for capacitor the current always leads. So yeah, that's it for my explanation for part C. Thank you.